Next we discuss application to this equation Ax congruent to B mod M. This is as a consequence of Euler's and Fermat's theorem. We can easily prove this theorem. Let M be a positive integer and let A belongs to Zm be relatively prime to M. Okay. We choose any A which is relatively prime to M. That means GCD of A comma M is equal to 1. Obviously this is A is not a zero divisor, consequently A is a unit in Zm. What does it mean? This A belongs to the group Gm. Okay, that means there exists an element A inverse belongs to Gm such that A multiplication modulo n A inverse that is equal to 1. So this is the meaning of this. Then if you assume this A, then Ax equal to B has a unique solution, because if Ax equal to B implies that by multiplying A inverse on the both sides, so A inverse multiplication modulo n Ax, okay, Ax means A into multiplication modulo n x, okay, equal to A inverse multiplication modulo n B. Obviously we know that this A inverse A gives 1, therefore x equal to A inverse B. Actually this product is multiplication modulo n, which shows that x is equal to A inverse B. Obviously A inverse B is a member of Zn as well. That means every equation Ax equal to B has a solution in Zm. This is not n, this is m. So we can easily prove that this is also a unique solution, because if you have suppose x1 and x2 are two solutions of the same equation, then if x1 and x2 are solutions of the same equation, then what happens? Ax1 is congruent to B, equal to B, and that is also equal to Ax2. Okay, then that is A into x1 minus x2 is equal to 0. But we know that since the A is a non-zero quantity and A is relatively prime to M, then this A is not a zero divisor. So when you multiply this A with any non-zero quantity, that never gives 0. So it is obvious that x1 minus x2 should be 0, because if x1 x2 is non-zero, then A is non-zero, this is non-zero, then product is 0, then A is a zero divisor. So we start with GCD of A comma M is equal to 1. So this A never be a zero divisor. For a zero divisor, that GCD must be greater than 1. So which implies this x1 minus x2 equal to 0. Otherwise this A would have been a zero divisor. So that will be a contradiction. So we can say that x1 minus x2 equals 0. So x1 equal to x2, which shows that if there exists two solutions, then they are the same. So this is the theorem 20.10. Okay. So next we prove the consequence of this theorem as well. Next we prove theorem 20.12. In this theorem we consider again the equation Ax equal to B. If D is the GCD of A comma M, the previous consequence we prove that if D is equal to 1, then it has only one solution, concurrent modulo. Then if the GCD is not 1, if suppose GCD is D, then there exists a solution if and only if D divides B. Okay. So if we have X equal to in order to prove this if and only if criterion, first we assume if D divides B, then Ax equal to B has a solution. If D does not divide B, then Ax equal to B has no solution. Okay, so we start with D does not divide B. Okay, we will prove that Ax equal to B has no solution. Okay, for that we assume, if possible, assume that there exists S in Zm such that As equal to B. Okay, we need to prove that there is no solution. So if you assume there is a solution S such that A is equal to B. Okay, but we know that GCD of A comma M is equal to D, which shows that you can write this is equal to what is the meaning of this? Ax equal to B implies As minus B equal to 0 in Zm. In Zm, 0 means multiple of. Okay. 0 in Zm means a multiple of M. So which shows that M divides As minus B. Okay. So As minus B is a multiple of M. We know that D divides A and D divides M. So from this you can write, or from these two statements are same. So As minus B equal to some K times M. We know that D is a GCD of M and A. So D divides M and D divides this A. Okay. So from this you can write what is B? B is equal to As minus Km. But A and M are divisible by D. This implies this right hand side is divisible by D. Then D is divisible. D divides B, which is a contradiction, because we assume that D does not divide B. So if you assume D does not divide B, then the existence of solution is not there. If there exists a solution, then that D should divide B. Okay. Conversely, suppose that D divides. Okay, D divides B. We will prove that if D divides B, then there is a solution. Okay. If D divides B, then you consider you write this A is equal to A1D, because D is the GCD of A comma M. Okay. D is the GCD of A comma M. So A is a multiple of D. This M is also a multiple of D. So A can be written as A1 into D, and this M can be written as M1 into D. And we also assume that D divides B, then B is also written as B1 times D. Okay. Now you consider, we need to show that this equation Ax equal to B has a solution. So how will you write that equation? We write this equation as we consider Ax equal to B. Okay, or we consider the equation Ax minus B equal to 0 in Zm. Obviously this Zm means this 0 in Zm means Ax minus B equal to, we are seeking for the solution of this. Okay. So Ax equal to some K times M in K times M. Okay, that's enough. Now you replace this A, B, M, okay, as or using this equation. So that is A1D x minus B1D equal to K into M1D. Okay. So this would imply that A1 x minus B1 equal to K into M1. Okay. Obviously, this we are seeking for the solution of this. If an x satisfies this condition, then x should satisfy this condition. Here we know that the GCD of A1 and M1. Okay, how will you get A1 comma M1? is nothing but a by d comma m by d. This GCD is 1. We already proved that if you consider a1x equal to b in Zm1, okay, if you consider this, then we can easily get the solution for this, because a1 GCD of a1 and m1 is 1, then this as a solution is a m1. Okay, so there exists, that means there exists an integer s such that a1x a1s minus b1, this is also b1 is a multiple of, okay, it's a multiple of m1, okay, or this is k times m1. Now you multiply this equation with the d, then that will be a1d s b1d is equal to k m1d. What is a1d? a1d is a into s minus b1d is b, that is equal to m1d is m, so this is equal to km, which shows that there exists an integer s such that as minus b equal to km. So this is a solution. That means if d divides b, then this equation has a solution. If d does not divides b, then this equation does not have a solution. This is the first part of the theorem. Now we need to show that exactly d solutions are there. Okay, we already proved that there is s such that if d divides, if this is the case, if d divides b, then there exists s such that a1 s minus b1 is a multiple of m1. We already proved this. Okay, so using this s, we can define numbers s plus m1, s plus m2, etc. Sorry, s plus m1, s plus 2m1, all the way up to s plus d minus 1. Obviously, all these satisfies the equation ax equal to b in Zm. Okay, because if s satisfies this, then what happens when we consider this a into s plus m1? You can easily prove that since this s is a solution of this, obviously this s plus m is also a solution of this. Okay, so we write this, since s is a solution of this one, then a1s minus b1 equal to k. Similarly, a1, what is s plus m1 minus b? This can be written as a1s plus a1m m1, okay, minus b. But we know that a1s, okay, minus, this is also b1, this is b1, a1s minus b1 is a multiple of, that is equal to km1. So we can write this km1 plus a1 m1, again this is a multiple of some k1 m. Okay, again this is a solution of this. Okay, so as this s is a solution of this equation, or a1 s minus b1 is a multiple of m1, you can get a1 times s plus m1 is a multiple of m1 again. Similarly, a1 times s plus m2, s plus 2 times m1, this is also a multiple of m1. Okay, so minus b1 is also there, minus b1. Okay, so if we choose any element of these, okay, any s plus some I times m1, so that will give a multiple of m1. So this minus b is also there, minus b1 is equal to multiple of some ki times multiple of m1. So if we multiply this equation with a d, we multiply equation with a d, for the first term will be a1 into d, that is a s plus I m1, okay, that is I m1. If you multiply d with the first term and d with the second term, you will get minus b1 times d, that is b, and multiply it with the right hand side, then that will be ki times m1 into d, that is m. That means this is the solution of ax minus b congruent to 0 mod m. That means all these if we start with 0 plus s plus 0 times m1, so there are d solutions are there. So these are all solutions of this equation. So once you assume there is a or d divides b, or there is at least one solution, then you can think of this d solutions. All these d solutions are incongruent. That means you cannot get this I times m1 congruent to s plus some j times m1. This is not possible. Okay. So if you can easily prove that these are incongruent. M1 mod m. Because if this is true, then if this is congruent, I m1 congruent to s plus j m1 mod m, then what happens? By taking difference, we will get I minus j m is congruent to 0 mod m. This is m1. Okay, you will get this one. So this implies I is congruent to j mod. If I and j are same, then only, or this is in fact this I and j are the same. I and j, I equal to j. Okay. Otherwise, if I and j are distinct, then m1 times I minus j will not be a multiple of m. Okay, because this we know that m1 times d is m. Okay, so m1 times any number I minus j is always less than d, because we take s plus 0 m and s plus 1 m and s plus 2 m, etc., etc. So 1, 2, 3, etc., all the way up to d minus 1. So if we, I comma j comes from this set, so I minus j or j minus I is always less than d, so that never be this never make a multiple of m. So I equal to j, that is the only possibility to get this is 0. So we know that this is always incongruent. So whenever this happens, then you can easily get I equal to j. So which shows that if d divides b, then exactly d solutions are there. Okay. As a consequence of this, we can prove corollary 20.13. That is, actually this is the corollary. If d be the GCD of positive integers a and m, then congruence x congruent to b mod m has a solution if and only if d divides b. That is what we have proved in this theorem. Okay. Then this is the case, that means d divides b the case, then solutions are the integers in exactly d distinct residue classes. D distinct residue classes means these solutions are from distinct residue classes. That means they are not congruent. That is the meaning of distinct residue classes. So we need to write this proof if you ask to prove this corollary. So the proof of the corollary is the same as this thing. So you need to write only the congruences instead of equal to sign. Okay, that is the thing. So with this we can conclude section 20. In the next class we start ideals of a ring. So that is a particular kind of subgroups or subrings of a ring. So along with this we can conclude section 20.